So last time we talked about really sort of redox reactions, and again, just to make sure everybody's sort of on the same page on these things, a reminder that when we talk about oxidation, it basically means usually that something loses electrons. If something loses electrons, it does become more positive. Um, a couple other definitions that we really don't run into all that often in general chemistry, but you do in sort of organic chemistry. Um, Oxidation also means that something gains oxygen as it goes from, say, reactants to products. Something loses hydrogen or H2 as it goes from reactants to products. And reduction, on the other hand, is again something that will gain electrons. Also, basically has the opposite definitions for hydrogen and oxygen. If something's being reduced, it means it will lose oxygen as it goes, say, from reactants to products. And if something is being reduced, it will gain hydrogen as it goes from, or H2 as it goes from reactants to products. So remember as well, we talked about the oxidizing agent. The oxidizing agent is the substance that is getting reduced. It is found on the reactant side, and the reducing agent is the substance that is getting oxidized. It's found on the reactant side as well. What helps us sort of determine what's happening sort of in terms of oxidation and reduction is basically the oxidation state. So we talked about last time as well, how to properly assign oxidation numbers. Usually if there's oxygen involved, you want to kind of start with that. And it's usually -2. You can kind of go to there's kind of 3 elements there. To the left-hand side, leave the guy in the center. And remember, the oxidation states are not necessarily the charges that we normally associate with an element in an ionic compound, although they can be the same. They are sort of the charge, if you want, in that element, and its sort of arrangement, how it's sort of put together in a particular compound. We also talked about balancing simple sort of redox reactions. By the way, those things always happen together. So if something's being oxidized, something is being reduced. So they do happen together. And the nice thing about that is if you can basically figure out, which one is being oxidized, you can just as easily figure out which one is being reduced, because it would be the opposite guy obviously doing that. So when we have just basic redox half reactions, oxidation and reduction half reactions, we want to make sure before we add them back together that the electrons are the same in each of the half reactions. When we have more complicated ones where we balance it in their basic or acidic solutions like we went through at the end there last time, it does involve balancing with oxygen using water, adding H plus and OH minus as well. So when it's all said and done, though, as we talked about last time, and you balance sort of this redox reaction, it does need to be balanced basically 2 ways. Balance like a normal equation, the same number of elements on each side, and also balanced in terms of charge. So the overall charge on the reactant side should match the overall charge on the product side. The charge does not have to be 0 on both sides, but it does just need to sort of match up. Any questions on that? All right, so we did one together last time, so why don't you try this one here? Here we want to balance this guy in basic solution. So take a few minutes, get started on it, and then we'll kind of pick it up here and make sure hopefully everybody's heading down the right direction. Here, we basically want to split it off into its 2 half reactions. So the very simple way of doing that is just really the 2 things that look alike. So I on one side, I2 on the other side. We also have Mn in this guy here, a little permanganate, and MnO2. We could also sort of figure out what is going on in terms of oxidation and reduction at this point. If we look at this guy here, the I has an oxidation state of -1, and the iodine there is 0. Remember, we could just use a simple sort of number line to figure that stuff out. I minus is -1, heading towards 0 is heading in this direction, becoming more positive, which means it is going through oxidation. While if we look at the Mn over here, oxygen is -2. There's 4 of them, which means -8, means the Mn here is like +7. And on this side, -2 for the oxygen gives us a -4, and +4. So if we look at sort of the Mn started at +7 over here, heading to +4, which is in this direction, which becomes more negative, which means it's going through reduction. So this should be our oxidation half reaction. This should be our reduction half reaction. Also means that the I here would be our reducing agent, and the Mn here would be our oxidizing agent in this case. Any questions on that so far? All right, so the first thing we want to do is really just kind of balance it up, kind of like a normal equation. So with that being said, we obviously need to put a 2 in front of the I since there's 2 of them over here. Down here, there's only one Mn and one Mn on both sides, so that's all good. We don't have to do anything there. I'll get this stuff out of the way. So the next thing that we want to do is balance the oxygen. So the top one has no oxygen, so we don't have to worry about it. Bottom one has 4 oxygens on the left, 2 on the right, which means we need to put 2 waters on the right-hand side to balance out the oxygen. When we do that, we're not only adding the oxygen, but we are adding 4 hydrogens, which does need to go to the other side. So we are not short in terms of hydrogens, and they go on as H pluses in this case. Any questions on that there? All right. So now that, yeah, go ahead.
Oh, sorry, wait, could you explain again why you added the 2 waters molecules?
Yeah, so the first thing we want to do is balance all the other elements other than oxygen and hydrogen, and that's why we put the 2 in front of the I. After you do that, you want to balance the oxygen and make sure that each side of the half reaction has the same number of oxygens. So what we started with in terms of oxygen is 4 on the left and 2 oxygens on the right. So to balance out the oxygens, we put the 2 waters because that's going to give us basically 2 oxygens. And that'll give us a grand total of 4 oxygens on the right-hand side, which will match the 4 oxygens on the left-hand side. And by the process of adding water, we're also adding, in addition to oxygen, hydrogen. So that's why we add 2 waters. 2 times 2 is 4 hydrogens on the right. That's why we also need to put the 4 H pluses on the left. Otherwise, if we don't do the H pluses as well, on the left-hand side, we will end up with not the right amount of hydrogens when it's all said and done. So the water is basically there to balance out the oxygens.
Okay, so you can't just add oxygens. You have to do you have to add H2O.
You do. So that's sort of the process of how to balance these guys. Is the way that we balance oxygen is basically to add however many waters that you need that will give you the oxygens, total that you're looking for. And for every water that you add to one side, the other side should get 2 H pluses, again, to keep that hydrogen balance as well. Other questions on that?
So from what I'm understanding, do we always do these redox equations that balance these redox equations like they're in acid solution, and then if it's asking us to find it in basic solution, we just
so there's actually multiple ways you can actually do these, but the simplest way to do it is to balance these guys in acidic solutions, and then at the end kind of turn it into a basic solution. There is a method where people kind of do the hydroxide adding in the middle, and sometimes it gets a little bit confusing because there's a lot of hydroxides and canceling and stuff that happens. So usually in my experience, the simplest approach, even though it's basic, which is ultimately what we're looking for here, is to actually just do it in acidic solutions, and at the end kind of turn it into a basic solution. But to be truthfully honest with you, people will do the basic part of it in the middle sometimes, but in my sort of watching it and doing it, it does end up with a lot of waters that you make and a lot of canceling you make and a lot more opportunity for mistake. So I think it's just a better approach to do it acidic and then turn it into basic. Other questions on that? Okay. So at this point, we have balanced all the oxygens, we balanced all the hydrogens, all the other elements. What we are looking to do now is actually balance out the overall charge. This also is sometimes done a different way or a couple of ways, but the simplest way that you hopefully won't make a mistake is just to look at the overall charge of what's going on in each side. So on the left-hand side of the first one, we have 2 I minuses. So that's like a grand total of -2 on the left-hand side. Right-hand side, all we have is I2, which has no charge. So overall on the left-hand side, we have a -2. On the right-hand side, we have 0. We need it to be the same on both sides, and we're adding electrons, which means we do need to add a couple of electrons here to the right-hand side, and that would get us an overall charge of -2 on the right and -2 on the left. We also should feel kind of good about that because we put the electrons on the product side, which is what should happen in an oxidation half reaction. Also why it's important to kind of know, what half reaction you're dealing with at that point. Now, over here, if we look at the second one, and again, sometimes people go individual element here and figure out what's happening, but honestly, you don't need to do that because the overall charges on all these guys takes into account everybody's oxidation numbers anyways. So overall here we have +4, even who cares what the Mn is here or the O4, the overall thing when it's all said and done is a -1 when it all comes together. And that's going to give us a -3 overall on the left-hand side. Right-hand side, this is 0, right? No charge. This is 0. So the side that needs the electrons in this case is actually going to be our left-hand side over here, which will need 3 electrons. That now gets us, I'm sorry, I actually learned to add, that's +3. And +3 and -3 gives us 0 on the left-hand side and 0 on the right-hand side in this case. So again, we ended up with the same charge on both sides. Any questions on that there? All right, now that we have the same number of electrons in each half reaction, I'm just going to rewrite it over here to get rid of all the sloppy stuff I've been writing, I guess. We have that. And on the other side, we have this. All right, we want to add these back together, but as we talked about previously, before you could add them together, you do need to make sure you have the same number of electrons in each of them. Here we only have 2. Here we have 3. So we actually need to multiply the top reaction by 3. That will give us 6 electrons in the top reaction. We need to multiply the bottom reaction by 2. That will give us 6 electrons in the bottom reaction. And if I do that and just recopy, doing our first one there, multiplying that 3 to everybody gives us 6 I minuses, goes to 3I2 plus 6 electrons. Multiplying the 2 to everybody that's there gives me 6 electrons plus, looks like 8 H pluses plus 2 MnO4 minuses. And coming on the other side there, 2 MnO2 plus 4 waters. At this point, the electrons should always cancel out. They should always be on opposite sides of the arrow. And anything else that could cancel, we could cancel, but it doesn't look like there's anything else. So everybody on the left-hand side stays on the left-hand side. So 8 H pluses plus 2 MnO4 minuses plus 6 I minuses go to 3 I2 plus 2 MnO2 plus 4 waters. At this point, this technically would be balanced in acidic conditions. Any questions on that so far? And again, we should be balanced both ways at this point. 8 hydrogens on both sides, 2 Mns, 8 oxygens on both sides, 6 iodides on both sides. Grand total of charge on the left-hand side, 8 positives and 8 negatives is 0, and 0 on the right-hand side. So if we were doing this in acidic solutions, we actually would be done at this point. Any questions up to here?
How do you know that it's acidic?
So this is just a process to balance one of these sort of redox reactions in acidic conditions up to this point. The reason you do know it actually is acidic if you're done at this point is actually looking at the equation. There's H plus. So that is
Okay.
That's a big hint that that you balanced it in acidic conditions through this process. And this process should get you always to sort of what the answer would be in acidic conditions.
Okay. And then, but we're going to basic solution because it's asking that. But if it was asking acidic, then we could just stop here.
Yeah. So if it was acting acidic, you could basically put a box on it and you would be done at this point. And again, because it is basic, we do have to do one more sort of step at this point. And again, this is again the sort of the easiest approach to do it acidic. And now that we wanted to make it basic, when we make it basic, what we're going to do is basically add OH minus to both sides. So how much OH minus do we add? It's actually the amount of H plus that we ended up with. So in this case, we ended up with 8 H pluses, which means when we go to add our OH minus, we're going to add an equal amount of OH minus, again, not to just one side, but to actually both sides in this case. What that's going to do is the side that has the OH minus and the H plus, those guys will then come together to make water, and it'll be like 8 waters in place of the 8 H pluses and 8 OH minuses. At this point, what typically happens when you add that hydroxide is you will form water on one side and you'll still have some water probably on the other side. So these guys at this point can cancel or reduce down. So there's 4 on one side. We'll then turn our 8 waters into 4 waters. And at this point, that should be it. And we could rewrite this. So we'll go like right here, maybe. So we're left with 4 waters plus 2 MnO4 minus plus 6 I minus. I'm going to run out of room, so I'm just going to go underneath. On the other side of the arrow, we will end up with 3I2 plus 2 MnO2 plus 8 hydroxides. At this point, this should be the balanced equation in basic conditions. And we could check that we are still balanced by making sure we have the same number of guys, same number of elements on each side. So let's take a look. We have 8 hydrogens on the left, 8 on the right. We got 8 oxygens plus 4 more is 12 on the left. 8 oxygens plus 4 more is 12. 2 MNs, 6 I's on both sides. Grand total charge on the left-hand side of the arrow is a -2 and a -6, which is -8. Grand total charge on the right-hand side of the arrow is -8 from the hydroxide. And to sort of answer a question earlier as well, we now know we are in basic solution, right? Because we now have hydroxide in that equation and no H pluses in that particular equation. Any questions on that there? So this, I think, is really the easiest way to balance something in basic solution. Like I mentioned earlier, sometimes people will kind of, before you add the electrons, add the hydroxide in and make water and stuff like that. But it does get a little messy if you sort of add the hydroxide in earlier on, because again, you make a lot of waters. There's a lot of reducing down that you have to do. And again, a lot more room for error. So it's a much better approach, I think, just going straight through, do it acidic, and then at the end, add your hydroxides, a lot less sort of canceling and stuff like that. Any questions on those steps there? Okay, why don't we try one more just to make sure. We'll skip this one. Let's try this one here. Let's balance this guy in acidic solution, see what you come up with, and we'll talk about it here in just a second. Chromium, so Cr2O72 minus going to our Cr3 plus. We also have our oxalate there, C2O42 minus, going to our CO2. Both of them have carbon, which is sort of the thing that ties them together. Again, it's always probably a good idea to kind of figure out what is going on here in terms of oxidation and reduction. So perhaps you remember this guy is a +6 oxidation state. That's a -2 for the oxygen, gives you -14. And that leaves us a -2 left over. So a +12 is what we need there. This obviously has a +3. So again, if you just kind of follow here, we're going from +6 to +3, which is moving in that direction, becoming more negative, which means it's actually going through reduction. While if we look at our oxalate, that is going to be -2, that's -8. So that's like a +3 probably. So +6 and -8 gives us a -2. Oxygen -2, -4, +4. So in terms of the carbon, it's starting at +3 and going to +4, which is moving in the right-hand side direction or becoming more positive, which means it's going through oxidation. So that's our oxidation. That's our reduction. That means the dichromate would be our oxidizing agent. And this guy here would be our reducing agent, the oxalate. Any questions on that there? Okay. All right, so I'm just gonna kind of erase some of this stuff here. So I got something I could see here. Get rid of that there. Maybe get rid of that. Get rid of that. And get rid of that. All right, so what we want to do here is, as we talked about previously, we want to just balance everything other than oxygen and hydrogen. So in this particular case, I got 2 chromiums on the left, so I will need a 2 there. I also have 2 oxygens on carbons on the left, and that means I would need a 2 there as well. At this point, we now want to balance our oxygens. On the top equation here, we got 7 oxygens on the left, none on the right. So that's going to be 7 waters. Because we added the 7 waters there, we will need to add 14 hydrogens, again, for the 14 hydrogens that came in from the water. Going to our bottom one, we got 4 oxygens on the left. By actually putting the 2 in front of the carbon here on the right, that gave us 4 oxygens on the right. We actually don't need to add any waters in this case because it kind of balanced itself out in that particular instance. At this point, we are ready to add electrons. So again, easiest thing to do is just look at overall charge happening here on the left-hand side. Looks like a +12. That's a 14 for the H pluses and a -2 for the dichromate. No need to go individual on everybody because the -2 takes into account everybody's individual oxidation state. Over here, that is a +6. That means that we will need to add 6 electrons to the left-hand side. And by earlier determining that this is our reduction half reaction, that should make sense because we're adding it to the correct side here. Any questions on that there? Overall charge, again, on the bottom guy, who cares what the carbon oxygen is individually here? Overall, it's a -2. Overall here is a 0. So to get to -2, we will need to add electrons to the right-hand side. Also looking good because that is the product side, and this is our oxidation half reaction. Remember, we should never add to the same side. They should always cancel out. Because of that, we do need to make sure we have the same number of electrons on each half reaction. We obviously have 6 here, but we only have 2 on the bottom. So we do need to multiply the bottom half reaction only in this case by 3. And I'm just going to rewrite the top guy there. I didn't do anything to it, just rewriting it here. Plus that.
And could you say again why you're multiplying by 3?
Yeah. So really at this point, what we want to do is basically take these two reactions and add them together. Because this is a redox reaction, what that really means is somebody will lose a certain amount of electrons, and those same amount of electrons should be gained by somebody else. And what that really means is when we look at each of the half reactions, before we could add them back together, because redox oxidation reduction happens together, so whatever electrons are lost has to be gained by somebody. So what that means is both of these half reactions do need to end up with the same number of electrons. And in this case, there's 6 in the first one, but only 2 in the second one. So in this case, if we multiply the second half reaction by 3, that will give us 6 electrons all the way across, and along with everybody else, obviously. And that will allow the electrons basically to be canceled. And basically what you would be saying in this case is the oxalate there lost 6 electrons, and the dichromate gained the 6 electrons basically. And so it's that kind of even transfer of electrons from one to the other.
Okay, thank you so much for explaining that.
Other questions on that? Okay, so, and again, that's why we did multiply by 3 here. So we're going to, and the important part is not just the electrons, but we want to multiply everybody in the equation by it. So multiplying that 3 all the way across gives us 3 of our C2O4 2 minuses, gives us 6 of the CO2 plus 6 electrons. And now because we did that, we now basically have the exact same amount of electrons in the reduction half reaction as we do in the oxidation half reaction. And it's really all about balancing, as I mentioned earlier. You know, the amount of electrons lost by somebody will be those gained by the other. And that now will allow us to add these together. Should always happen in redox reactions. The electrons should always completely cancel out because of that. And in this case, I think that is all that will cancel. So that will leave us something like 14 H pluses on the left, plus a dichromate, Cr2O7 2 minus, plus 3 of the oxalate. On the right-hand side of the arrow, we will end up with 2 of the Cr3 plus 7 of the waters, and 6 of the CO2. And in this particular case, this would be balanced in acidic conditions. Again, we know it's acidic conditions because there's some H pluses there in the overall reaction. So that tells us it's acidic. We could double check to make sure we did okay on balancing. 14 H's on the left, 14 on the right. I got 7 oxygens here, and 12 more is a lot, but I think that's 19, I think. And 7 oxygens and 12 is 19. 6 carbons, and 2 CRs, 2 CRs. Grand total of charge is -2, and -6 is -8, plus a 14. That is like 6, I think, +6, and +6 on the right-hand side. So it would be balanced in this case, again, in acidic conditions, as we see that H plus in the overall reaction. Questions on that there? Obviously, if we wanted basic at this point, we would add 14 OH minuses to both sides. It would create 14 waters, which would get reduced down, and that would then convert it into basic. Any questions on how to balance these equations? Okay, so again, I just want to make sure everybody's sort of on the same page in terms of doing this. And again, it kind of depends, I suppose, on who you had or where you took the first semester. Sometimes people do a lot of this. Sometimes people just kind of brush over it. So hopefully either it helped you or it's a good review, I suppose. All right, any questions on this stuff before we continue on with the kind of the stuff that's related?
Sorry, could I ask one question about it's the +12 and the +6. How did you find that it was +12? Was it because the hydrogen? Yeah. How did you find that?
So the easiest way when you're kind of doing charges, and sometimes people will say, well, you should look at each individual element and figure out what's being oxidized, reduced, what's their oxidation states, and you really don't need to do that. So when you look at this is basically 14, and this overall guy is +1, so that's like a +14. This entire thing here has a -2 charge, so that's where the -2. That -2 takes into account everybody's oxidation state, so no need to redo the work there. This overall thing here, the oxalate has a -2 charge, but there's 3 of them, which gives you a -6 overall. So in that case, if you kind of add that together, that's -8 and +14 gives you a +6 overall sort of charge, if you will, on the left-hand side. If you go to the right-hand side, this guy is 0 as it has no charge as water. CO2 is 0. This chromium here has a +3, and there's 2 of them, which gives you a +6 charge overall. And on the right-hand side, it's overall +6. Left-hand side, it is overall +6. And that is what you're looking for when you balance these redox reactions. Again, they don't have to equal 0 on both sides. They can equal the same number and charge. So in the sense of it could be +2, +2, -2, -2. But the overall charge on each side just needs to be exactly the same. Other questions on that?
Okay, thank you so much.
You're welcome. Any other questions on these balancing here? Okay, so we're then going to talk about galvanic cells, which are really just redox reactions sort of run in beakers and in the lab and so forth. So let's talk about those. So a galvanic cell is really, as I mentioned before, just a redox reaction that's happening, sort of happening within a cell that's in a laboratory a lot of times built out of beakers. And we have a couple of different things. We have some electrodes here, some solid electrodes that are typically included in the galvanic cell. They're usually hooked together by some type of wire. It kind of goes through a voltage meter, which will give you the voltage of the cell. There's also a bridge here that typically will combine or sort of connect both sides here. And that is what's referred to as the salt bridge. The salt bridge typically will have some type of ionic solution in it, basically a positive and negative sort of solution. Now, the left-hand side, and that has to be the left-hand side, I suppose, but we'll go on this picture here. This is what's known as the anode side. And on the anode side, that's where oxidation occurs. That's where we're going to lose electrons. So what happens is if you take something like zinc, which is solid, on the electrode here, and it basically will become zinc with a +2 charge and lose a couple of electrons. Now, what happens here, as you can see in this sort of blown up picture, is essentially when the zinc loses those electrons, it comes out of the solid phase and basically goes for a swim in the liquid. Those electrons then travel along the wire to the other side of your galvanic cell, which is known as the cathode side. And at the cathode side, that's where reduction takes place, which means we have a gaining of electrons happening here. Now, what happens in that case is those electrons come on in. We have some solution floating around that has the ion. That's the same metal as the solid. Gains those electrons, becomes a solid, and kind of comes out of solution. So we typically have the anode side where oxidation occurs, usually comprised of an electrode, solid version of, say, the metal or whatever may be going through oxidation. Usually in the liquid part are ions present of that electrode. On the other side, we have our cathode, which also contains a liquid that contains basically the positively charged guy that's equal to the solid guy that's there. Now, this flow of electrons, right, creates some voltage, as we see. And and we'll get some positive voltage, usually means pretty good. What is the purpose of our salt bridge? Well, the salt bridge kind of keeps everything flowing, if you will. There is sort of a overall, if you want to think about it, kind of a positive difference on the cathode side, and that's what sort of pulls those electrons from one side to the next. Now, if we did this without the salt bridge, right? So if we kind of did this cell without like the salt bridge doing that, let's just think about what's happening in terms of charge. Well, we have electrons coming this way into our cathode, right? And our anode. And because the electrons are coming this way, those ions are dropping into solution. And that's building up a big old positive charge here, right? If we didn't have a salt bridge. On the product side, or the cathode side over here, we're having all those positive guys jump out of solution, which means we're building up a negative charge over here. So what would happen if we didn't have the salt bridge? Well, we would build up a negative charge. Would that be good for negative electrons trying to come this way? They're going to go, no, thank you, because that's negative and negative interaction, which they do not like, which means the electrons actually will want to go and stay over here. And the cell would kind of cease to run very efficiently at that point. So what helps us with that? It's actually our salt bridge, as you can see here. In the salt bridge, you can see the positive guy actually heads over here. What does that do? It cuts down on all that negative charge, right? Kind of keeps the positive a little bit higher. The negative ion heads over to the anode side, also going to cut down on the positive buildup here. And that's going to allow this cell to efficiently operate over a good period of time without getting sort of a buildup of charge that you really don't want. So again, without it, we would really get a buildup of negative charge on our cathode side, which essentially would stop the flow of electrons happening there because you wouldn't have this sort of greater positive side over there. And it actually would keep the electrons on the anode side. So that's really the function of the salt bridge, is to kind of maintain the balance of charge on each side of the cell, not to allow one charge to build up too much on one side versus the other, and kind of stop those flow of electrons. Any questions on that there? So on our cathode side, obviously in this particular example, we have our electrons here, which is our reduction, going to solid copper. If we add up our overall sort of reaction that's happening here, this is sometimes referred to as our net ionic equation that's sort of taking place. We can see pretty much our redox reaction that's happening. Overall charge on our zinc here, oxidation is 0 to +2. So again, becoming more positive and going through oxidation. Copper is going from +2, oops, grab the wrong thing there, do that, +2 to 0. And obviously going from +2 to 0 on our number line, becoming more negative and going through reduction. So this is the overall process that's happening in this particular cell. And again, we would look at the cell voltage there to help us determine whether or not this reaction would be spontaneous. As we'll talk about here in this chapter, a positive voltage does sort of mean a spontaneous reaction occurring. Any questions on a galvanic cell? So you do need to know what's happening at the anode side, the cathode side, just what's happening with the salt bridge, and again, sort of what the general setup of a galvanic cell would look like in the laboratory. So speaking of one that's sort of in the laboratory, that's sort of what it would look like if you built one in the laboratory. You can see a couple of things here. Obviously, you see our two beakers like we talked about. Again, in the solution here would be the ions floating around. That's the same as the metal that's there. It's probably zinc. And over here is our copper. And again, our blue copper solution, which has ions floating around. Hard to see in the picture, but there actually is a salt bridge right about there that's connecting both of those beakers. And you can see you can hook it up with some electrodes. The electrons sort of transfer from our anode to cathode. And again, we get our positive voltage here of 1.1 volts in this particular case. Now, the difference in electrical potential between the anode and the cathode is sometimes referred to as the cell voltage. A volt is basically 1 joule of work per coulomb of charge transferred. Coulomb is a C, it's a unit of electrical charge. 1 volt is equal to 1 joule over coulomb. Is sometimes referred to as well as the electromotive force, the EMF, or the cell potential. The cell potential is sort of what I was talking about. You know, there is sort of a, more if you want to think about it, kind of a positive aspect on the cathode side versus our anode side. And that difference in sort of the charge on one side versus the other is going to help kind of bring those electrons over, through the wire. Those three things are oftentimes used in questions and they basically mean the same thing in the sense of a question. If you're asked to calculate the EMF or the cell potential or the cell voltage, usually they want you just to figure out the voltage for the particular cell is basically what they want you to calculate. Now, there's also, in addition to sort of the overall reaction or equation for galvanic cells, another way that we demonstrated, and that's what's sometimes referred to as a cell diagram. And in a cell diagram, it is basically arranged like it is down here on the bottom. So how is it arranged? Well, it is arranged by anode first, followed by cathode. And what does each of these things sort of represent? Well, this first guy is usually your reactant. So that is your reactant. And then we have one line that basically kind of separates it into the product side of the reaction. So if you look on the product side, there is the zinc and there is the zinc. We do include the molarity here of obviously the solution is 1 molar in this case, and that's why it's included in there. So that's typically how sort of these cell diagrams go. We go reactants, products, reactants, products in that sense. And we can see that same pattern happening here on the other side. When we get to our product side, we have our copper, which is on our product side, our reactant side. And then we have our solid copper, which is on our product side there. On our product side. What does the 2 lines sort of in the middle represent? The 2 lines in the middle represent the salt bridge. So that represents the salt bridge. So this is sort of your anode compartment, if you will, on the left-hand side, and your cathode compartment on your right-hand side. And if you had just a cell diagram given to you, that's essentially how you would turn it into an equation. You would start on the left-hand side and go, okay, the first guy is a reactant. The second guy is a product. The first guy over here after the salt bridge is a reactant. Second guy is a product. So reactants, products, and again, that's how you could go from your cell diagram into your actual equation. Any questions on that there? So you do need to be able to write a cell diagram. You do need to be able to go from a cell diagram to an equation to a cell diagram. Other things that sometimes do pop into a cell diagram are things like pressures. If you're dealing with gases, which sometimes happens with galvanic cells, sometimes there's gases involved. So sometimes you'll see pressures. You'll also sometimes see things like platinum, as we'll see here in just a second, or something like that, some type of solid electrode that's being used because either the anode or cathode is a gas or something like that. There's no solid version of it. So let's take a look at one of those. So for example, here, if we hook up zinc with a hydrogen electrode in this particular case, we end up with this reaction here. Our zinc is our anode, and our cathode is our hydrogen here, which is our H+. And again, we can see a couple of things sort of in there that's a little bit different. Overall reaction, this is our reactant, that's our product. If we come down here, that's our reactant, that's our product. This is our reactant. This is our product. Right? And again, that's how we go from our cell diagram. The difference is here, hydrogen gas is a gas. So there's a couple of other things involved here. We have the pressure, which is standard pressure of 1 atmosphere. And we have one additional thing here, which is a platinum. Now, the platinum is not really part of the reaction. It is sort of the physical electrode that is being used here, as obviously it's a gas and there is no sort of physical version of it. So you'll sometimes see some extra things in these cell diagrams. And again, sometimes there's a physical sort of aspect of it. What's happening here is sort of the same thing. We got our zinc that's basically dropping out into zinc ions. Electrons are coming around because there's hydrochloric acid, which is a strong acid. There's a lot of H pluses floating around. Electrons come in, and we basically make H2, right, which is our gas that's bubbling out in that solution. So again, here we also have, again, our salt bridge, which is going to keep that sort of balance in charge and allow this cell to continue to run from one side to the next. So that's why, again, our oxidation here is our zinc, losing a couple electrons, H plus from the hydrochloric acid in the solution that's floating around, picking up a couple of those electrons, producing the hydrogen gas that you see actually bubble off here. Any questions on that there? So how do we know sort of these half reactions? What are sort of their value in terms of voltage? And that is what is sometimes referred to as standard reduction potential, is sometimes referred to as the SRP value for standard reduction potential. So much like a lot of things in chemistry and so forth, you know, they need to sort of assign something as a standard to compare everybody else to. And in the case of these sort of SRP values, they assigned a hydrogen as the standard, and it has a cell voltage of 0 volts, an SRP value of 0. This is what is sometimes referred to as the She electrode for standard hydrogen electrode. And basically, they take this hydrogen electrode, they assigned it a value of 0, and basically hook it up with all kinds of other electrodes and basically get the cell voltage, and they're able to determine what is the SRP value for, you know, all the other sort of elements, if you will. Now, there's an importance of this name, and the name is SRP, which stands for standard reduction potential. And what that means is when we do these SRP sort of equations, they are all written as reduction reactions, electrons on the left-hand side. So because a galvanic cell really is a redox reaction, and because that means there has to be an oxidation occurring, when we use SRP values, technically speaking, one of the values will be wrong the way they are written. They will be written as a reduction reaction when in reality what's happening is an oxidation reaction. So what I mean by that is we will see a table here in just a second. But if we went to the table, we would find zinc written like this, which is a reduction reaction, and it would have an SRP value. We would also find, obviously, hydrogen, as we just saw, written as a reduction reaction. Well, clearly they both cannot be reductions, and clearly, as we know here, this is actually an oxidation. So there's a couple of things that you have to kind of keep in mind when you kind of look up these SRP values. Is technically speaking, one of them will be incorrect in terms of what's happening in the galvanic cell, because what's happening is an oxidation reaction rather than a reduction reaction. And how can we figure out what's happening on the other side? Well, there's actually an equation here that we could use. And this equation is E of the cell is equal to E of the cathode minus E of the anode. We would find these values on an SRP table, which we'll see here in just a second. Now, I'm going to tell you something about this equation right now, which may not make sense to you right now, but hopefully it'll make sense when we kind of get there. If you use this equation and you go to the actual SRP table and you find the two things in your galvanic cell, you should not change the sign. So you should not change the sign on the anode reaction if you use this equation. The reason for that is that's why I subtract here, because it will actually change the sign for you. If you want to change the sign, which is correct, you should do this equation and actually add them. And again, may not make sense to you right now, but hopefully it will in just a second what I'm talking about. So if you add, you should change the sign. So I'll just put that up here so I remember to say it. So let's look at how we could use this sort of equation here. We hook up a cell like zinc and our hydrogen. Again, the zinc being our anode, the hydrogen being our cathode. It has a cell voltage of 0.76 volts. Putting that into our E of the cell, which would be 0.76. And obviously, in this case, our cathode is 0. Gives us a SRP value for zinc of 0.76, negative 0.76. Again, we could take our standard hydrogen electrode, hook it up with something else like copper here. And when we hook it up with copper, what we end up getting is a cell voltage of 0.34 volts. Different though in this case is the hydrogen here is actually the anode and the copper here is our cathode in this case. And that also demonstrates something that, you know, anything can be an anode or cathode. You could hook them up any way you like, anode or cathode. Just in certain cases, it may work in terms of a spontaneous reaction. In some cases, it may not work. How do you know it doesn't work? You get negative voltage. And if you get negative voltage, all you do is basically switch them around and your negative voltage will become a positive voltage in that particular case. So you can pretty much hook anybody up you like in terms of being the anode or cathode. How you know sort of which one is working properly in that sense is that, and positive voltage is usually that good sign that you're looking for. So this is essentially how they came about figuring out all the SRP values. It is a big table of SRP values. And let's talk a little bit about that table here. Here's sort of a table of all these SRP values. A couple of things on this is, again, because they are all reduction, these are all written as reduction half reactions, which means that in certain cases, we do need to flip around this reaction to really do it correctly. When we flip it around, we actually do change the sign of it. So here's this. So let's talk about some of the values that you find on a table like this. First off, when we see the E value or the SRP value, it's for exactly how the reaction is written. Not that you can see this reaction, it's not important, but it is written as a reduction reaction. You know, how do we know when we're pulling off an SRP table like this one or the previous one that we saw, you know, which one is our anode or cathode? So if you are not given any information about how the reaction is taking place, you can use the SRP values and compare them, and it will tell you which one should be your anode and which one should be your cathode. The more positive E value that you find on the table has a greater tendency to be reduced. So which thing gets reduced? That is your cathode. So in a lack of any other piece of information given to you, like the overall reaction, Like it specifically says, this is the anode, this is the cathode. If they don't tell you anything other than, hey, you just made a galvanic cell with these two things, you could go to the SRP table. The one that is more positive should be your cathode. The one that is more negative should be your anode. These half reactions are reversible. When you reverse a reaction, you basically change the sign of it. So earlier, let's see if we can find it right there, zinc. So earlier we were talking about zinc being our anode, right? And if we look at this reaction, again, it's written as a cathode. So if we wanted to reverse it like it really was happening in that reaction we were looking at, it would look something like this. What does that do to our E value? If we reverse it, the E naught for this reaction written like this would actually be positive 0.76 volts. Okay. Now, I'm going to explain to you what I was talking about earlier. So let's just say we took, we'll do the copper and the zinc right here. We're going to do a cell of these two things, okay? And we're going to say our zinc is our anode and our copper is our cathode, right? So we'll do it that way. So what's going to happen in this case is we're going to use that equation that we saw earlier, which is E of the cell is E of the cathode minus E of the anode. Okay. Now, technically speaking, like I was saying earlier, if we use this equation and we're going to subtract, we would simply go to this table and find those two values. And we would see that, again, our cathode is copper, which means we would end up with 0.34 volts minus the value that we find for zinc in the table, which would be minus 0.76 volts. And that obviously would get you 1.1 volts positive in this case for our cell voltage. Now, what I did here is I subtracted, so I took the table value just the way it was, even though technically this reaction was an oxidation reaction, right? Now, if you want to write everything correctly, you would reverse that reaction like I did on the screen here on the left. We would also take our copper, which is our cathode reaction, which looks just like we find it on the table. And our E naught would be 0.34 volts. In this case, my anode reaction, I reversed it. I changed the sign. What I should do in this case is add them together. I should take 0.34 volts plus my 0.76 volts, which gives me obviously our 1.1 volts, which is positive in this case. Now, the reason I say is if you want to write the equation correctly, and technically zinc going to zinc with a +2 charge has an E value of plus 0.76 volts. Zinc with a 2+ going to zinc with no charge has an E value of -76 volts. But if you change the actual value that you find in the table for the anode and switch the sign, you should add them together. And that is why when we do the subtracting part, we don't change the sign, because the subtraction will change the sign of the anode. So my recommendation is this: choose a way. So if you want to change the sign, add them together, the values. If you don't want to change the sign, you should subtract them. Don't do both, otherwise you'll screw it up. So you could do it either way, but that's why it's cathode minus anode, because you could just simply go to the table. You don't have to worry about switching the sign, because the subtraction will switch the sign for you. Technically speaking, if you want to write everything correctly, you should switch the sign and add them together. So your call, however you want to do it. I would choose one way and stick with it. Any questions on that? Again, you just don't want to switch the sign and then subtract it, because then you will unswitch the sign, obviously, if you do that. Any questions on sort of that equation that we saw earlier? Okay. The last thing that we do with these numbers as well is sometimes, as we talked about when we're talking about balancing redox reactions, right, you need to multiply a half reaction by a common number. And what that does is it actually will have no effect on the SRP value that you find in the table. So if you need to multiply a half reaction by 2, 3, whatever it may be, it will have no effect on the value you find in the table. So you do not multiply the value in the table by that coefficient. Any questions on that there? Okay, so we're going to lay it up there for today as we